on the strong density conjecture for Apollonian circle packing.
So thank you very much to the organizers for the invitation and for putting on this lovely workshop. I just wanted to say a word about the notation. So when we first started out this business, I guess it was called affine linear sieve. And since then, it's gotten a slightly more, Yeah. But so I wanted to relate that I was having lunch with Peter Sarnak maybe a year ago or so, and he said, there's this, he wants to call this expansion property very strong. There's weak approximation, strong approximation. He wants to call it very strong approximation. So I said, well, there's strong rigidity and super rigidity. Why don't you call it super approximation? And now we have a conference on super strong approximation. So may I recommend again that, anyway, just a comment. So I'll be speaking about Apollonian circle packings. You already heard what they are. In fact, let me show you a picture. So he showed some beautiful pictures of circle packings, but one thing that wasn't mentioned is the arithmetic properties of circle packings. So everybody probably has seen these pictures, but let me just put it up. So here's again some packing. And I'll write in some numbers here. So this is 23 and 27 and 18. I forget what the outer one is. Maybe minus 14 or so. So the outermost circle has opposite orientation. So these are the curvatures, these numbers that we were talking about. So the curvature or the bend of a circle is just 1 over its radius. And he was discussing various counting problems when you consider the circles. But there's a whole other set of counting problems which were addressed in this paper. So Ligarius, Mallows, and Wilkes started studying these things and then picked up by Graham, Ligarius, Mallows, Wilkes, and Yan in a whole series of papers, I think around 2003, made some beautiful conjectures on what are the integers that arise as you continue this operation. So let me just introduce a little bit of notation. So as in He's talk, we will have this root quadruple. So V naught is the root quadruple. It doesn't matter which 4 circles you take, but let's just take the 4 largest ones. That's actually what the root quadruple is defined to be. So these are just the 4 smallest curvatures in whichever order you like. And so given such a packing, given an integral packing, so this is an Apollonian circle packing, such that for all circles in the packing, the bend is an integer. So this is called an integral packing. We define the set of bends the set of all integers which arise as curvatures in the packing. So is that clear, the definition? Now, as he pointed out, there's this quadratic form. So let me write it up again. This is Descartes' theorem. That if V, which is A, B, C, D, for some reason I want these to be column vectors, is a quadruple of mutually tangent circles, is the set of bends of a quadruple of mutually tangent circles, then we have this relationship. I'll put up the quadratic form again. ABCD is equal to twice the sum of the squares minus their sum squared. And the theorem is that these points lie on the cone, Q equals 0. So a consequence of this, so corollary, if we fix A, B, and C, then you just have a quadratic formula telling you what D is. And everybody knows how to solve a quadratic formula. There are two solutions. There's D plus and D minus, right? Negative B plus or minus square root of just the quadratic formula. So in fact, the fact that there are two solutions is just another restatement of the theorem of Apollonius. Given three circles, there are two others that you can fill in. And moreover, if you add the two solutions, the square root sign cancels, and it's an elementary exercise from here, that you get twice A plus B plus C. So what that means is if you want to go from the element A, B, C, D plus to the element A, B, C, D minus, you can do it by multiplying by a matrix which leaves A alone, leave B and C alone, and replace D plus by two A's, two B's, two C's, and a minus 1 D plus, and that'll get you D minus. Okay, so this is the element, let's call this S4, and it's exactly, I mean, we're realizing explicitly the representation that he was talking about, where if you take these circles and look at one of the dual circles, so take 3 points of tangency and look at this dual circle, then reflection through the dual circle leaves alone A, B, and C, and sends D plus to D minus. So this is geometrically a reflection, which we've realized algebraically. So we're realizing explicitly this representation from SL2C into SOQ, which has signature 3-1. Okay? Is that clear? I think almost everybody here is familiar with this, so I'm just wasting it. Okay, so this is the element S4, and of course there are these other elements, S1, where you flip the element A, so leave everybody else alone, and so on, S2 and S3, S2 and S3, and it's clear what S2 and S3 are. And so we can introduce, again, the Apollonian group. So definition, gamma for us will be the group generated by S1 up to S4, and this is a subgroup. Well, it's almost it's not SO, but it's OQ, because they have determinant -1. These are reflections. It's a Coxeter group, in fact. And the observation is that these matrices are integral. So it's not just in OQR, but it's in fact a subgroup of OQZ. Okay? So when he said that you can look at the orbit, all of the quadruples that arise in the packing, so let's define the orbit of quadruples. The orbit of quadruples is exactly the action of gamma on V naught. Okay, so this is the set of all A, B, C, D, where A, B, C, D are 4 mutually tangent circles in the packing. The curvatures of 4 mutually tangent circles in the packing. Any questions? This is elementary, right? So then we can realize this set of bends, the set of all possible bends, well, they arise as some entry in this set of all quadruples. So then we have the elementary observation that the set of bends is equal to, well, I want to pick off all the possible entries. So let's use, E1 is 1, 0, 0, 0. So if I take the inner product of E1 with gamma V naught, or I take the inner product of E2 or E3 or E4, so just pick off the coordinates in the orbit, and that's exactly the set of all curvatures in the packing. Okay. So now let me tell you what the conjectures are. So here's the conjecture. So to state the conjecture, I need to give another definition, which is, so the 5-author paper, they already observed that there were some congruence obstructions to integers appearing in here. And so we let A be the set of admissible numbers. So this is the set of integers, so that N is in the set of bends mod Q for all Q. So obviously, if you're not in the set of bends mod 16, you can't possibly be one of the representable numbers. And then here's the strong density conjectures. So this is the strong density conjecture of these 5 authors. Is a local to global principle. And the local to global principle is simply that whatever number is not excluded by local obstructions should be there. Well, there might be, the circle 12 might not be excluded by local obstructions, but that circle's too big to fit in the packing. So let's ignore some small finite number of points. So an integer which is admissible and sufficiently large, which could depend on the packing, that integer is the curvature of some circle in the packing. Okay, so this is the strong density conjecture. And already in this paper, they made some progress towards the strong density conjecture. Well, I don't have to assume primitivity because that will be captured by the local obstructions. But you're right, I might as well assume primitivity so that the local obstructions are as small as they possibly could be. So what he is pointing out is that if I shrink this all by 2, then all the bends double. So then everybody's even. But that's not as interesting a situation, so we'll always assume by rescaling that the GCD of the bends is 1. So the first progress on this work is already here, which is, so I need another definition. So let's call this set Bn, so I don't have to write it every time. So this is the set of all bends up to n. And what they prove is there are at least root n elements in here. So let me explain to you the proof because it'll be relevant for us. They make the following observation. Okay, we can't get our hands on this group gamma, right? It's some infinite index subgroup of the full orthogonal group. If we had the full orthogonal group, this becomes a classical question. The local to global principle, representations of quadratic forms, Kloosterman's method will exactly tell you what's going on in 4 variables. But we don't know what's going on in this thin group gamma. But what they observe is this group, despite being thin, has some parabolic elements, has some unipotent elements. And unipotents give you an injection of affine space. So what they observe, let's take this element, I don't know, let's call it M. So let's take S4 times S2. So I can even tell you what that is. I woke up at 3 a.m. this morning, New York time, so let me not try to do 4 by 4 matrix multiplication in front of you. If I'm not mistaken, it should be that matrix. Okay. Well, there's a conjugate. There's some element, some matrix J, which I could also write down for you. And its conjugate, the conjugate of M under J, can be expressed as like so. So now it's blatantly clear, blatantly obvious that this is indeed a unipotent element. And now let me remind you of the representation, the spin representation from GL2R, PSL2R into SO21, which I'll embed in GL4, which takes alpha, beta, gamma, delta to 1 over the determinant gamma squared, beta squared, delta squared, and then there's some elements here. I don't really care what they are. Okay, so there's a spin this is just the classical spin representation from SO21, from PSL2R into SO21, realized in this way. And what you see is that the pre-image of this element M tilde, I guess I need to tell you just a little bit more about it. So this is 2 beta delta, and this is alpha beta. Then you can read off right away that the element, so observe that if you take the element 1, 2, 0, 1, starting here, is sent by rho to the matrix M tilde. Okay? Well, why am I writing all of this? It's that powers of unipotent elements are trivial. So I know exactly what happens if I take this to the nth power. To the nth power is just that. So we have an injection of the affine line. What that means, when you take this element, map it by rho, you get some n and n squareds here, and then you undo the conjugation, and you find that the powers of m look like so. I just care about the bottom row. So it's 4n squared plus 2n is the first entry. And the second entry is 4n squared plus 2n. And then negative 2n and 2n plus 1. So it's clear what's going on? Yes?
So where are those guys? If I charted those circles,
Yes? So all you're doing is flipping through this circle and through that circle. And then you flip back through this circle and through that circle. And back through this circle and through that circle. In fact,
They're just the little circles piling up at a point of tangent.
yes, exactly. So the easiest place to see this is in the infinite packing, where you have if you write down these numbers, it's 1 and then 4 and then 9 and then 16. You have the squares going down into this cusp. So this is just some matrix. You can take a matrix power without going through all this representation theory. The point is, this is for every n, this is some element in the group. But that means that m to the n times v naught, which will be, I don't know what the first three elements look like, but the last element looks like 4n squared a plus b plus 2n a plus b minus c plus d. I'm just giving it to you explicitly because you can write it down explicitly, plus d. For every n, this will be a quadruple in the orbit. In other words, for every n, this, which we can just write as an squared plus bn plus c, it's just some quadratic. What we found is values of a quadratic polynomial lying inside the orbit. But that immediately tells you that there's square root terms in it, up to n. Okay, so that's the first theorem. That's the first progress. Progress 2 is in a letter of Sarnak, from Sarnak to Ligarius on Sarnak's website, which take this observation just one step further, is let's have another matrix, M prime, which is not S4 times S2, but S3 times S2. And if you do the same conjugation, so theorem, the theorem says that the number of points is almost n over, is almost n. It's almost a positive proportion. It's n over root log n. And the proof is that if you take this other matrix, then you take the same conjugate, and you look at the inverse image, it's the element, it's some other parabolic element. Okay, but once you have this element, and you have this element in the pre-image of the same conjugate of gamma, you have the group generated by those two elements. But that group, so the group, remark, the group generated by, this is Lubotsky's 1, 2, 3 that we saw earlier today. At least in PSL2, this is exactly the congruence 2 group, the classical congruence 2 subgroup of SL2Z, PSL2Z. So what that means is not only do you have the injection of one entry, this implies that for any matrix of the form x, y in gamma 2, so x has to be even and x and y have to be relatively prime, but ignore those for 1 second. You can take rho of this matrix and conjugate it, or conjugate it, inverse conjugate it, and this will be an element in the group. And I can tell you what it is, and it looks something like x squared plus xy plus y squared minus 1, x squared plus xy minus xy, and xy plus y squared. So this is just some explicit computation. Okay? Yes, exactly. Exactly. So geometrically, in fact, this is how you should have known that this is going to be a congruence group, or at least that it's gamma 2. You can see it right here. Let's take all the circles that are touching the outermost circles. So this element will fix the outermost circle. This element, this dual circle, will fix the outermost circle. And so will that circle. So these three transformations, 1, 2, 3, all fix the outermost circle. So we can use the outermost circle as the boundary of hyperbolic space, which we can think of as the disk in here. And now we see that a fundamental domain is exactly this ideal triangle. But that's gamma 2. The only thing that isn't obvious a priori is that, okay, there are ideal triangles, but is it an arithmetic triangle? And it turns out it is. So we have this, so we know exactly that these elements, every element of this form, for any x, y, for any integers x and y with some simple restrictions, there will be an element of this form in the group gamma. And that means that there will be an element in the orbit so that means that the orbit contains that element times your ABCD, which when you multiply it out, I don't care what the first three entries are, but the bottom entry is some quadratic in x and y, actually shifted quadratic. Shifted binary quadratic. And that means, because the bends are just the values of the orbit, if I take the inner product with E4, that the set of bends contains the set of values of this shifted binary quadratic for all xy. And it goes back to Landau. So if you just look at x squared plus y squared, that goes back to Fermat. What numbers are represented as sums of two squares? Well, the prime 3 mod 4, it causes a problem. So if you sieve out half of the primes, you lose a root log. And that's exactly star next to you. Okay. That's just using this group. So we cooked up this group. Let me call the image, so definition, the image of rho of gamma 2. So I take this full congruence group, and then I take its conjugate. So this is some group which I'll call gamma 1, which sits inside the Apollonian group. And this group is just this group, so it's some copy of SO21. So inside this infinite volume hyperbolic 3 manifold is actually a finite volume arithmetic hyperbolic 2 manifold, which you can also see geometrically if you want in hyperbolic 3 space. So if I take the packing, which is this infinite packing, then the dual packing will have fundamental domain, which is these geodesic planes, and then 2 geodesic hemispheres. And if you cut this one hemisphere along that vertical line, there again is your copy of the hyperbolic 2 manifold sitting inside the hyperbolic 3 manifold. Okay. The next progress was made in the thesis of Elena Fuchs, 2010, 09, 10, 10, which is that the number of points shaves something off the root log. So instead of log to the half, it's log to the 0.1, 0.15. And finally, so this is now combining these. You see, if you just take this group gamma 1 and act on the root quadruple, you get one set of values of these shifted binary quadratics. But you can also change what the quadruple is by moving to another quadruple. And so that's exactly what's done here. And then Bergan and Fuchs 11, let's say 11, solve the positive density conjecture. So rub out the log altogether. So a positive proportion of the integers are curvatures in packing. Okay. Now let me just restate this conjecture. So the conjecture is every sufficiently large integer should be in the packing, should be a bend of some circle. So let me restate the conjecture, the strong density conjecture, in the following way. The number of points, the number of elements in the bends up to n should be equal to the number of admissible numbers up to n plus an error of size 1. That's just a complete restatement of the previous theorem. And let me point out that in Fuchs's thesis, she also analyzed exactly what this admissible set is. I have to specify. A priori, it looks like there's infinitely many, it's a condition on infinitely many elements. But actually, this group, which is Zariski dense, if you reduce it mod anything relatively prime to 6, you're completely onto the corresponding reduction in OQ. And the primes 2 and 3 cause a problem. The prime 3 stabilizes at the power 9, and the prime 2 stabilizes beyond 8. So 24, so A is determined given the root quadruple mod 24. So let me write that as the number of elements in A is just however many admissibles there are up to 24 over 24. So it's just a union of some arithmetic progressions with modulus dividing 24 times n plus big O of 1. Okay, so this is just saying that there's some arithmetic progressions. So of course, we expect the number of elements to be exactly this constant times n with finitely many exceptions, possibly. Well, not possibly. There are finitely many exceptions. And so the theorem, this is joint work with Schoen, I guess 12 now, is I'd love to put a 1 there, but the best we can do is a power savings. So this is a set of density 1 within the admissibles satisfies a local to global principle for the Apollonian circle packing with an exceptional set which has a power savings. Before I say how this is proved, let me just make one remark about what happens. So this whole story gets generalized to higher dimensions. There's Soddy. Actually, Soddy was the first one to even realize that there exist integral packings. So the Apollonian circle packing picture already appears in Leibniz's notebook when he's studying infinities. That's very old. He didn't call it Apollonius. I'm not actually sure when the word Apollonius first got attached to that picture. I think in the 80s or so, or 60s. Yeah, maybe it is. Maybe it is Mandelbrot, because the earlier literature discusses Apollonius' theorem and Descartes' theorem, but the packing I didn't see having that name. Anyway, but Soddy certainly was the earliest reference I'm aware of, in 1937 in his Nature poem, was the first to realize that there's an integrality here with the circle packings. So in higher dimensions, so in dimension n, you have the same story. So there's the Soddy-Gosset theorem, which is the analog of Descartes' theorem. There's some quadratic form, which 5 mutually tangent spheres, or n plus 2 mutually tangent n spheres, their curvatures lie on a quadratic form, which they write down. But if n is greater than or equal to 4 in hyperspace and higher, when you start with n disjoint hyperspheres and you start moving them around by these operations, you don't get a packing. The spheres start to intersect one another. Also, you lose integrality. The curvatures, even if you start with 6 mutually tangent 4 spheres that have integral curvatures, when you start moving them around, you lose integrality. But in dimension 3, the spheres. So 2-dimension, the space they're in. 2-dimension is a circle.
But also, there's no magic starting configuration which always gives you integral?
For dimension 4 and higher, so the corresponding groups that you would write down, in dimension 3, it's an integral group, and in dimension 4 and higher, it's just the entries aren't integers anymore. They're rational. It's an S-arithmetic group, but it's not integer. So there's no integrality, and there's no packing, in that the spheres start overlapping. But in dimension 3, you do have all of these phenomena. So let me show you a picture I found on the internet drawn by Joss Lays. So this is a Soddy sphere packing. And you might ask exactly the same question for Soddy sphere packings. So, theorem. This is from last year for Soddy sphere packings. The number of bends up to n is the number of admissibles. So a genuine local to global principle. And the argument is actually just Sarnak's argument. But what you realize is that you get not a hyperbolic 2. So here we get an arithmetic hyperbolic 2 manifold sitting inside an infinite volume hyperbolic 3 manifold. 1 dimension up, you get a hyperbolic 4 manifold, which is infinite volume. Sitting inside of it is a hyperbolic 3 manifold, which is arithmetic. So instead of having these coordinates, where with x's and y's, now x's and y's are complex numbers. And you have an injection of complex 2 variables, which is real 4 variables. So what you have in 3 dimensions is, so proof, same procedure, gives injection of values of quadratic forms, not in 2 variables, which would lead in Sarnak's estimate to this loss of root log, in 4 variables. And then Klusterman's method takes over. Okay. So this is just to point out that this problem is really delicate in dimension 2. This is the only case in which it's delicate.
Does this say, is this the same, or is this saying that not only do you get every admissible integer, but you get them all touching some fixed 3 sphere?
Yes. Not one fixed 3 sphere, because there will be some very small local obstructions in the one 4 variable form, quadratic form. But if you just wiggle it around a few steps, you fill out all the admissibles.
So is there a lot of repeating in the
Oh, tons. Yeah, of course. Yeah, because so as he said in her talk, so let me remind you, this was our work from, what do we say, 09? something like that. So let me remind you, and now we have power savings versions of this. The number of, so let me just write it down. The number of circles in the packing, not bends. So bends is counting just the integers, which is circles without multiplicity. But if you count the circles with multiplicity, with bend at most t, you get an asymptotic formula, ct to the delta.
How big is delta?
So in 3 dimensions, delta is 2.1 or something. It's bigger than 3/2, which is what you need for Patterson-Sullivan theory to kick in. So by the way, you can also prove, I wasn't going to go into it, but you can prove bounds on how many primes and almost, upper bounds, the same kind that, are you going to talk about the affine sieve part of it tomorrow? Maybe, maybe not. Yeah? So if you restrict to primes, we proved upper bounds which drop by log as expected.
So am I correct that you're saying within this you get a lattice that's comparable to SL2 of Z adjoined a cube root of unity? Is that right? Just as you got SL2Z here?
We got SL2Z here. What you actually find here is that inside this infinite index subgroup of 041 lives a group which is actually it's a Hecke group. It's a Hecke-Bianchi group. I don't have a good notation for this. It's a gamma naught of, in the ring of integers, Q adjoin root -3, where the C element is congruent to root 3. 0 mod root 3, mod the ideal root 3.
But after commensurability, it's SL2Z adjoined a cube root of unity.
Yes, yeah. Square root of unity. Cube root. Yeah.
It's the figure 8.
Yeah, exactly. Effective O1 from Klosterman. Klosterman's effective. The O. Yes.
Since
Yes.
delta is bigger than 2 now, you could ask about the distribution of pairs
Yes.
of radii.
Yes, there's all kinds of fun questions you can start playing with here. Yeah, absolutely. My point was just to point out that if you have enough unipotent elements, the problem becomes trivial after some computation. And it's only in this case where you have some unipotent elements and you can get started, but it's still very thin and you have to do something to get there's a quasi-local to global principle. Okay, any questions? So let me try to explain where all these things are coming from. So let me, I guess, relate this problem. So observation. This problem is exactly the same problem, sort of heuristically, as the problem Jean talked about, the Zaremba problem. So for Zaremba, you have this semigroup, we called it GA, which is the semigroup, I don't know how to notate this, semigroup generated by the elements 0, 1, 1, A going up to A, or living in some alphabet. And the interest, when you take words in these elements, you get the right column to be B on D. And D is the element that you're interested in. That's Zaremba's problem. And so Zaremba's problem is you take E2, inner product, GA acting on E2, and you want to know that this is full. This is all integers. And of course, this problem is the same. You have a group, you have some vector acting on it, and you have the projection on that side. So this is a semigroup. I don't have a good notation for this. Semigroup generated by these elements. The point is it's an orbit. So maybe better than affine sieve is orbital sieve. You have some action, and you want to take some elements in this orbit. Or the question that Kurt posed before was, or I guess we'll pose tomorrow, is about traces in such elements. These we can't touch. Our method really is using the bilinear structure. to get bilinear forms in the minor arc. So let me get into some of the specifics of what's going on. Any questions before I go? Yeah. Yeah. It'll still. That's right. There's a reduction here that's happening. Okay, so let me see. So, ingredients. I'll be more precise about the circle method in a second. But for the major arcs, we need recent work by my student Ilya Vinogradov on bisector counts in infinite volume, 3 manifolds. Hyperbolic 3 manifolds. So let me just recall that. So this is extending the work Jean talked about. So again, joint with Bergan and Sarnak, where we proved the same statement for 2 manifolds. So let me just state the theorem. So his theorem. So this is Vinogradov, is the following. What you'd like to do is take any orbit in the group whatsoever and decompose it into the action. So write G. So G for us will be SL2C. Write it in its KAK decomposition. So K here, of course, is SU2. And SU2 has Euler coordinates. So I can write this as MHM, where M is just the circle, e to the I theta, e minus I theta. H is SO2, and another copy of M. So actually, there's an M that can move through. There's the normalizer of A and K can move around. So really, what we want to write, each of these K's we'll write in this way, MHM. Then A, so A is the diagonal group, e to the t over 2, e to the minus t over 2. A plus, meaning t is positive. And then another K, M, H, M. But one of these M's, as I just said, is extraneous. Because this is a 6 real dimensional group, and I have 7 parameters, so I'll just arbitrarily rub one out. Okay? So if you look at K mod M, so this is SU2 mod essentially SO. So this is like SO3 mod SO2. This is a sphere, is a 2-sphere. It's just a sphere, geometrically. And so that sphere you can interpret as the boundary of hyperbolic 3 space in the ball model. On that ball model, we have Patterson-Sullivan measure, as he already discussed. And so this is K mod M. And this is K mod M from the other side. And so there's a Patterson-Sullivan measure on each of these. And so if you take some regions phi and psi in K mod M, let's say rectangular patches, and some interval I, some interval in 0, 1, and you want to count how many elements there are in the group. So each matrix we'll write as, let's call this pair S1. So it's some point on the sphere. This is little a. This is little m. And this is some other point which we'll write as S2 inverse because the m action flips to the other side. So if you look at the indicator function of S1, meaning S1 of gamma, being in this one region of K over M, the m variable, so let's go in order. The a variable being at most t, which is just to say take a k invariant norm, the m variable being in some interval I, and the S2 variable inverse being in some interval, in some range psi in k mod m, then the indicator function of this ensemble, so you have control on every single variable. You restrict this circle, this sphere, to some region. A is bounded above in a ball. M is restricted to an interval. And S2 is also restricted to the same region, to some other region possibly. Then this is equal to some explicit constant, which he writes down, some pi's and deltas. So delta is always the dimension of the group, times the Patterson-Sullivan measure of phi, times the Patterson-Sullivan measure of psi, times Lebesgue measure on the m variable, and t to the 2 delta, and an error term, which is a power savings depending on the spectral gap in the appropriate group. Okay, so this is the theorem. So it's a complete decomposition. So he and her work with Min Lee are decomposing G mod M. So they don't care about the M type when you take your first irreducible component, which is this infinite dimensional vector space, and you grade it by the K types. They only need the M invariant K types, but for our theorem, we actually need the full decomposition of the group. So once you have a theorem like this, any region you want to count, unless it's extremely perverse and has horrible boundary, which is not the case in the Apollonian setting, you can just use calculus to add up these slivers. And that's exactly what he's doing to get the power savings. So it's a completely different method from the one that Min Lee and he are using. Okay, so that's the ingredient for the major arcs. Now let me tell you what's needed for the minor arcs, and then I'll try to be a little bit more specific about what those mean. Well, let me just say that the minor arcs follow. So for the minor arcs, need to get some sleep. So the minor arcs, you need, so I guess this is 2, use recent work of Bergan in his, so this is 2011, in which he proves, so you can look not just at which integers arise as curvatures and try to get a positive proportion of the integers. You can look at which curvatures in the first n integers are also prime numbers. So just from Sornak's observation already, that you have this shifted binary quadratics, and Ivanyich's half-dimensional sieve tells you that you have at least, so the number of elements here is at least n over, so there were root log n elements, and if you sieve for primes among those, that drops by another log. And what Bergan proves is that you can remove this log. So you can remove the 1/2 power loss that you have. So a positive proportion of the primes appear in these curvatures using the circle method and using certain bilinear estimates related to this problem. Okay, so combining these two ingredients, the major arc analysis, which goes through spectral theory, and the minor arc analysis, which goes, it's actually somewhat classical, I mean, in flavor, not in execution, you get exactly this local to global statement with a power savings. Okay, so any questions? So what time do I? 10 minutes. Okay, great. So let's get into it. Let me try to write down some of the things that we want to use. So what we want to use is this group gamma 1. So let me give this element a name. Did I erase it already? I guess I did erase it, but let me put it back here. So this was some element with x's and y's, some explicit element with x's and y's that came as the representation of any element. If you recall, we have any element xy in gamma 2, and its representation, the spin representation, into SO21, and then conjugated gives you some element here. Let's give this element a name. Let's call it xy. So we know that for all integers xy with some congruence restrictions, there's an element of this form in the group. So here's a definition. So n will be our main parameter, and let Rn of little n be the number of times the integer n appears as, so if I just took v0 and acted on it by this element cxy, and took the inner product of that with e4, meaning took the fourth entry, that would exactly be that one fixed quadratic form, shifted binary quadratic. So that's if I summed over x and y, integers x and y, let's say of size some capital X. But we want to use many quadratic forms. So if you don't just start with the vector of A naught, B naught, C naught, D naught, but stick in here another element gamma, where gamma is genuinely in the group and runs over elements of norm T. So this is changing the coordinates, the coefficients, capital A. It's changing when I change what the vector is. Instead of having just the root quadruple here, I change which vector it is that I'm adding these Archimedean elements to. You change the coordinates of these elements. So if you combine both the full group setting and this Archimedean setting, then you get the representation function that we're interested in. Okay? So, yes, so this is exactly a family of quadratics. Because as gamma ranges, for each fixed gamma, you get a quadratic form, values of quadratic forms in x and y. Yes. Yeah, I'm getting there. Yeah. The bilinear nature is that this inner product can be separated. So we're going to use this in two ways. For the major arcs, we're going to use the fact that there's a gamma here. For the minor arcs, we're going to use the fact that there's a xi here. And play those two off of one another. Okay, so let's just get a sense. So capital N is how big little n should be, roughly. So these elements, remember, these elements have an x times y and an x squared in them. So if x and y are roughly capital X, these elements are of size big X squared. And this is an element of size t. And this is an element of fixed size. It's just the root quadruple. So what we'd like is the parameter capital N to be x squared t. And we'll get most of the mass out of the Archimedean, out of this, out of affine space, and just some of the mass out of the group. So we'll set t will be roughly n to the 1 over 100, and x is almost as big as root n in our parameters. Just letting you know how the parameters will look. Okay, so this is the main, so the observation, of course, is that if this number is not 0, then n is a bend in the packet, just because both of these are elements in the group. Okay? So let's take the Fourier transform of this. That's a function on the circle. So it's just the sum over gamma, the sum over x and y. And e to the 2 pi I theta times this integer, e4 inner product cxy gamma v naught. So trivial Fourier analysis tells you recover Rn from R hat with an integral on the circle. So that's completely trivial, but what isn't completely trivial is Hardy and Ramanujan's initial idea that you can capture the modes of this thing. The harmonics of Rn will be large near rational numbers with small denominators. So it's prudent to decompose this as an integral over the major arcs plus the minor arcs, which is just the complement of the major arcs. So we'll call this the main term plus some error term. Now, in the interest of time, let me not go too much into the main term, except to say, if you look at r hat n of p, so let's just say theta is equal to a rational number. So these will be, the numbers here will be rational numbers with small denominators, very close to rational numbers with very small denominators, with the parameter, just as Jean was talking about in his lecture, which now will be some small power of n, which will depend on the spectral gap. Of course, the spectral gap is coming from the work of Bourgain, Gambart, Sarnak. Then if you look at what this is saying, it's a sum over all gamma, sum over x and y. Well, let me put these in the opposite order. I'll just put in the definition. E of theta, which is r over q, and E4 inner product CXY, gamma V naught. But of course, this, because we have an x, this is e to the 2 pi I theta over q. So it only depends on the residue class of gamma mod q, which means you should break this sum. So you write gamma as the q congruent subgroup of gamma times the quotient. So here, this gamma depends only on this quotient, and then you have to sum over this gamma, and this is exactly where the spectral theory comes in. And what you're able to prove is that this main term, so theorem, this main term for n of size capital N is exactly as large as it should be. So it's some singular series which will depend on n, which will see exactly the failure of gamma mod gamma q to be onto for all q. The only q, so q mod 24 determines, if q is divisible by 24, it determines exactly what these quotients are. Otherwise, these quotients are all of O, the orthogonal group preserving the Descartes form, times what it should be. And what it should be is, so I guess I didn't say how large, how much mass do we have to play with? How big is this at the origin? Rn hat of 0 is roughly of size, well, so 0 just means how many numbers are there to play with. There's x squared terms here, and the number of terms, the number of elements in gamma in a ball of size t is t to the delta, where delta is this dimension, 1.3. So you see the integers are of size x squared t, but the number of points we have to play with is x squared t to the delta. So we have a few more points to play with than the size of the integers. And remember, t is quite small relative to n, but it's still some power of n. And so what you expect here is how many points we have to play with. But of course, this should be equidistributed. So we should divide by how many points there are total, and that's x squared t. So we expect exactly some singular series, which will vanish if n is not admissible, times t to the delta minus 1. Okay, so we're not capturing all of the points we should because t is much smaller than n, but we'll use the Archimedean, this affine piece, to be able to say something along minor arcs. Okay, so any questions about how the major arcs? You'll get something that's, I believe, it's something like 1 over log n. Yeah. So it really can't hurt these powers. Okay. And of course, as you might imagine, now you need to count these weird regions in the group. So this was just at the one rational point, but now there's, of course, a plus beta here. And to really remove the modular and Archimedean components, you need the full force of this bisector counting theorem. So that's exactly where this applied to congruence groups with uniform bounds. So of course, this theta depends on the spectral gap. So all of that is going into the major arcs analysis. Yes, yes, of course. Yeah, so I should say yes. Yeah. So now you'd like to control the error term. And if you could prove, so if this error term is little o of t to the delta minus 1, then you're done. You've actually proved the strong density conjecture. Because just make n sufficiently large that the main term is always bigger than the error term, and this number can't be 0, and so you're there. That seems very hard to do. And in fact, so this is what I was saying in our GAFA paper. We have, well, we can show that for certain values of n, it will be as large as the main term. So this is when the major arcs are fooling you into thinking you have numbers when they aren't there. So this will imply the full strong density conjecture, and this is too strong. So what we can prove is an L2 estimate, just like what Jean was talking about, which the sum of the squares of these, again, by Parseval, is the, so this is the integral along the minor arcs, so this will be an integral along the minor arcs of Rn hat squared. And what's the trivial bound on this? Well, the trivial bound on R hat n is R hat n at 0. So that's x squared delta. And we have that squared, so that's x to the 4th t to the 2 delta. And we need to save a whole power of n and a little bit. Okay? So it's I mean, if you want to think about it, on average, for each of these, you need to save a root n and a little bit more than root n for each of the 2 copies of R hat that you have here. Then you save an n and a little power. What does that tell you? How much time do I have? Finish up? Okay, so let me just say why that will imply the main theorem. So assuming this theorem, then look at, so proof of the main theorem, look at the exceptional set. So how many numbers there are up to n which are admissible and for which you don't have a local to global principle in the sense that the exceptional set, or this error term, the error term is bigger than how big the main term should be, which is t to the delta minus 1. Right? So if this thing that's supposed to be an error term is bigger than the main term, this is the size, this is an upper bound for the exceptional set. So let's replace 1 by something bigger than 1. So this is n going up to n. I'll square, so the fact that this divided by this is bigger than 1 means I can put t to the 2 delta minus 2 there. That's an upper bound. And then let's stick in this upper bound, and you get x to the 4 t to the 2 delta over n to the 1 plus epsilon, and t to the 2 delta minus 2. And if you work that out, you should get n to the 1 minus epsilon. Okay, so let me stop there. Thanks.